All right, thank you very much, Julia, and a big thank you to all the organizers for the enormous effort it takes to put on the annual Amplitudes conference for the first time in Asia. And I'm here representing years of experience as maybe the oldest person in the room. I think you know, and you don't beat me, no. So I'm going to talk about share with you my obsession in the past couple of years, which has been this thing we discovered in one particular setting called antipodal self-duality. And I'm going to apologize for the fact that it's in planar n equals 4 super Yang Mills. And maybe apologize even more that in trying to find other examples of it, we turned to an even simpler model than planar n equals 4 called Fishnet theory. And the cast of characters in Fishnet theory will be some 4-point functions that involve two scalar fields dotted and dashed and solid lines here that form these grids, which you can see why they're called fishnets. And so this work was done recently with Claude Dour, but I'll also review some of the work in planar n equals 4 leading up to it. And if there's a few minutes at the end, I'll tell you about some follow-up work we've been doing with with a student. So let me just give you sort of the outline and summary. There's a very strange symmetry that occurs in some form factors and amplitudes in planar n equals 4. And what is strange about it is that it doesn't say that two things are equal. It says that two things are equal, but you have to do a transformation, which is called the antipode map on the Hopf algebra of multiple polylogs. But you've all heard about the symbol many times this week, and the symbol has a sequence of letters, and the antipode map essentially requires you to reverse the order of the letters. And so in order to equate two things, you have to first read everything backwards in order to get to the other side. And in the first case it was discovered, it was a duality between two different processes. But then we understood that those are kind of related to a self-duality of another process, which I'll get into. And this antipode map is kind of strange from the point of view of what it does to functions. The front of the symbol tells you where all the branch cuts are. The back of the symbol describes the derivatives. So somehow you're exchanging the roles of branch cuts and derivatives when you perform this map. And the new part of the work is to apply it in the fishnet theory. And in this fishnet theory, amplitudes are very simple, or things like amplitudes, like correlation functions, they can be just single diagrams. So now we have the opportunity to try to diagnose these integrals and see if there's some good reason, perhaps related to integrability, that is underlying this strange symmetry. So let's just talk about what it means to reverse words. I mean, you could reverse words and do nothing to the alphabet. In that case, it's called a palindrome. It's something that's the same backwards and forwards. So you can see I'm dating myself again. I should have used BTS, but I couldn't get it to work. So sorry. But you'll see that ABBA also knew they were a palindrome, since they even wrote the second B to reflect that. But what we're doing now is we're trying to do examples where you reverse the words, but you're allowed to do a map on the letters as well. So for example, suppose you want to reverse the word and have it come back to itself, but only when you also do a letter map. For example, D exchanged with R and C exchanged with D. Can you think of a word that is invariant under that property? Well, it's not really a unique solution, but I like this one. So you see, if you reverse the order, you also have to switch B and R and C and D to get it to work. So we have examples of symbols, which are linear combinations of up to 1 billion terms, where you reverse the order and you perform one of these letter map substitutions, and then it becomes a symbol for another process. And that's an example of what we're going to look at today. So this is the obligatory apology for doing planar n equals 4 instead of QCD like real physicists do. But Planar n equals 4 is the maximally supersymmetric cousin of n equals 4. And maximally supersymmetric cousin of QCD is n equals 4 super Yang-Mills theory. And as you all know, it has usually taken to have a gauge group SUN. And to make it planar, you take the large n limit. And then it has lots of great properties like integrability and uniform weight for all of its amplitudes. So in general, the amplitudes of any theory like QCD can be written as a sum over rational terms and transcendental terms. And there's often a very intricate interplay between these two pieces in QCD amplitudes. But in n equals 4, the rational structure is well understood and pretty much invariant from loop order to loop order. So we can just focus on the transcendental functions. And the simple processes we're going to talk about today all have essentially just one rational prefactor, which we divide out when we divide out the tree amplitude. And so everything's all about the transcendental functions for these examples. Also, there are infrared divergences for all of these quantities, but they can be divided out by some suitable ansatz like the BDS or BDS-like ansatz. So I won't talk too much about that, and we'll just discuss the finite remainders after we've removed all of the infrared divergences. So the overview of the setting of where we have seen antipodal duality and antipodal self-duality in the original planar n equals 4 is on this slide here. So we have, we first observed it by a total accident in the context of the 3-point form factor of an operator, which is one of the simplest local operators. It's the chiral stress tensor multiplet. So you could think of it as the trace of phi squared, where phi stands for a combination of the scalar fields in the theory, and this is actually a traceless in the flavor index combination to make it BPS invariant. And that's the lowest component of some superfield, and there's also other representatives involving the self-dual parts of the field strength. So, so this operator has some very nice matrix elements onto 3 gluon states, and that's called the 3 gluon form factor. And then it's related through this duality to the 6-point amplitude, I should say MHV 6-point amplitude, which has been studied for a while. And we had data up to 7 loops here. And then we constructed with Omer Gertigan and Andrew McLeod and Matthias Wilhelm, the latter two are in the audience. We constructed data here up to 8 loops. And then we found this duality that relates these two quantities. And this is a quantity that depends on 2 dimensionless variables. And here you live in a 2-dimensional slice of the 3-dimensional phase space. But then we realized that this duality was a reflection of a self-duality of another process. And this process is the 4-point form factor of this same operator. And in one limit, it becomes the 3-point form factor. When you take 2 of these gluons collinear and you work with a quantity called the remainder function, this 4 goes smoothly into F3. And it's a little more subtle, but in the triple collinear limit, this F4 actually goes at the remainder function level, goes into the remainder function for the 6 gluon amplitude. So we found a kinematic map that, when accompanied by the antipode map reversing letters, takes this object back into itself. And it works anywhere in this phase, actually in a slice of the phase space that has 4 dimensionless variables. But if you take one limit here, the map of the point of the limit here goes into this limit here. So this symmetry, this self-duality, explains this one. But we still don't know where this one's coming from. It's a total mystery. So that's the general outline of the situation as it stands for the case of the undeformed planar n equals 4. And then the other cast of the other arena in which we've now started to see this antipodal self-duality is a strongly deformed version of planar n equals 4. So without going into all the details, you can take n equals 4 and write it in n equals 1 superspace with a superpotential, and you can crank up the superpotential and make it very large. And it's also multiplied by the standard gauge coupling. So you take the gauge coupling to 0 as you take the superpotential very large and keep the product finite. But when you do that, the gluons don't see the superpotential. They only couple through the gauge coupling. So the gluon couplings go to 0. They decouple. And the fermions can also decouple in one of the limits. In one of the limits, you're only left with scalars, 2 of the 3 complex scalars, x and z. And this deformation, in order to retain integrability, you have to sacrifice unitarity. And so the superpotential has some complex phases in it, and it's non-Hermitian. And so you're left with a non-Hermitian coupling that looks like this. The conjugate would have a trace in a different order, but you don't include that. And because of that, when you have a line from z to z dagger, it can only intersect the line from x to x dagger in a particular orientation, which generally forbids bubble type diagrams. And so that, because of that simple interaction, when you try to compute a 4-point function with a certain number of lines emanating from, say, this operator x to the n of x1, there are n lines coming out of x to the n, and the only option for them is to be absorbed by this operator x dagger to the n after crossing the m lines that correspond to making and destroying the field z to the m. So you get a single diagram for these 4-point functions. And it turns out to be a very simple result to evaluate, although it looks pretty complicated at first sight. And because of the conformal invariance, this function doesn't depend on all 4 of these points. There are only 2 cross ratios that enter it, as in standard conformal field theory 4-point functions. And they can be further described here as cross ratios, u and v, but it's simpler to parameterize them in terms of z and z bar. So that will be the cast of characters in the second part of the talk. And all of the answers, all of the results for these amplitudes and form factors and correlation functions are multiple polylogs. And we've already heard a lot about them in these talks and others throughout the week. So I'll be pretty brief here. But in general, they're all described as iterated integrals, where you integrate a certain polylog, generalized polylog, with some indices and an argument t with a d log, in this case t minus a1, and that puts one more argument in front. So these multiple polylogs, we like to describe them with the hop algebra that was pointed out, in particular the symbol by Goncharov, Spradlin, Vergu, and Volovich. And there's a differential definition that leads to write the derivative of any function in the space as a sum over d logs of these sk's, which belong to some space L we'll call the symbol alphabet. And then this is called the first coproduct. If this has weight n, then this has weight n minus 1. And we've peeled off one weight in the logarithm. So we call this the n minus 1, comma 1 coproduct of f. So we can iterate this structure. Well, first we formalize it by writing the coaction as a splitting into a tensor product of lower weight things by just adopting the coefficients in the derivative here and then tensoring them with the logarithms of these symbol letters. And that's the first element, or one element, of the Hopf algebra that splits you into weight n minus 1 and 1. But then we can iterate it and do the same thing to this weight n minus 1 guy, FSK. and we take its derivative, and then we, or fsj, we do the same thing, and we then get a n minus 2, comma 1, comma 1 double coproduct here. And we keep iterating, and these have lower and lower weight until we've done it n times, if f had weight n, and then we get a tensor product here, and we usually drop the logarithm at this stage and just write the symbol letters, and their tensor product is here, and then these are all rational numbers. And in many cases, they will be integers if we normalize all the letters properly. So that gives us the symbol, which is celebrating its 15th birthday this year. So one simple example, which will be relevant here, is the classical polylogs. So the first classical polylog is just the logarithm, but at 1 minus x. And it's the integral of dt over 1 minus t. But if you then integrate dt over t times the classical polylog of weight n minus 1, that defines the one, oh, this should be an n. Lin of x is the integral of Lin minus 1 of t dt over t. And so then the derivative of Lin of x just gives us a d log of x and Lin minus 1. So according to the rules of constructing the symbol of Lin of x should be the symbol of Lin minus 1 of x tensored with the d log argument x. And then we can just keep iterating this down to lower, all the way down to the first entry, which is the logarithm of 1 minus x. So this is the symbol of Lin of x. And again, the branch cut discontinuities are displayed in the first entry. You see this logarithm here. It corresponds to a branch cut, which is where this series no longer converges at x equals 1. And the same is true for all the polylogs because they're found by integrating up the logarithm. And once you have that branch cut there, it just keeps staying there as you integrate up further. So the branch cuts are controlled by the vanishing loci of the first entries. And the derivatives are controlled by the back entries. And the alphabet is, in this case, is just x and 1 minus x. There are many other symbols you can write with just x and 1 minus x, and the classical polylogs are a special case of that. So the second example is actually built out of the first example, and it's the first fishnet integral, the very simplest one, where you just have one line going this way and one line going this way. And that's also known as the 4-mass box, and it's been known for many years. I learned at this conference that Andrew Hodges called it the dog function. But then Zagier called it the Bloch-Wigner dialogue after a paper almost the same time. So this Bloch-Wigner dilogarithm is actually a single-valued function in the complex z-plane. So if you go around z equals 0 or go around z equals 1, the branch cuts in z and z bar cancel each other. So it's very cleverly arranged, and it has to be in order to represent this kind of an integral. So it's this function here that involves dilogs and logs. And I should have said there's a couple properties of the symbol which are useful. If you have the symbol of the product of two transcendental functions, like log x and log y, you shuffle their individual symbols. And in this case, the individual symbols are just x and y. And shuffling means you write them down in all possible relative orders, which is just like this. Also, because the symbols represent logarithms, it's easy to see that if you have an xy there, then you replace it by the same object with just x plus the same object with just y. Anyway, if you use the fact from the previous slide that the symbol of Li2 is minus 1 minus z tensor z, and similarly for the z bar, and then you apply these rules for shuffling together the symbols of over here of the logarithms, you will pretty easily reproduce this formula for the symbol of the Bloch-Wigner dialogue. So the symbol alphabet in this case has 4 entries, z and 1 minus z, z bar and 1 minus z bar. And the single valuedness that I mentioned is the fact that in the first entry, z and z bar never appear separately. They always appear together. And similarly for 1 minus z and 1 minus z bar. Now, this integral actually has an antipodal self-duality. Let's look at it again. If we take the action of reversing the letter order in the symbol and combine it with a kinematic letter map that looks like this, it will be invariant. So this map is essentially complex conjugation. So z to z bar and 1 minus z to 1 minus z bar. But there's a slight twist to it in that you also have to flip over when you could choose to flip these over instead of these, but either one is sort of equivalent. And so the combined action we'll call S hat, and that's the antipodal self-duality. It involves the antipode symmetry map S of reversing the letter order, and also this map C on the letters. So let's see what happens when we apply it to this first term. So z and z bar, they map to z bar over z. And up to a minus sign, that corresponds to z over z bar. Flipping letters over gives you a minus sign. On the contrary, 1 minus z and over 1 minus z bar, that goes to the front on this term. So this term here, including maps into this term, including the minus sign. And similarly, you'll see that when you map this term back to the front, it goes into each other. So there's an invariance of that object. And by itself, that wouldn't be so interesting, but it turns out that this generalizes to arbitrary square fishnets. But we'll come back to that later for the arbitrary fishnet case. First, I just wanted to say a little more details about the 3-gluon form factor. As I mentioned, this is a function of 2 dimensionless variables, which we call u and v, and they are ratios of the dimensionful Mandelstam variables for 2 of the gluon scattering, say S12, divided by the q squared of the operator, which is also S123. So u is this dimensionless ratio, and v is obtained by a cyclic a cycling, which is the symmetry of the problem, 1 to 2, 2 to 3, 3 to 1. And then w is the third one, but there's a mass shell, a momentum conservation constraint that says that w isn't actually independent, but it's useful to keep it in there to expose the symmetries. When we look at the alphabet for this problem, which has now been computed up to 8 loops, it has 6 letters in it. And we can write them in terms of u, v, w, 1 minus u, 1 minus v, 1 minus w. But it's more compact if we switch to this alphabet in terms of A, B, C, D, E, F, which are defined in this way. And when we do that, the symbols of the this 3-point form factor at 1 and 2 loops are very simple. They're just 1 and 2 terms, plus their images under a D3 dihedral symmetry, which includes cycling and also flipping. So the 1 loop 1 just involves the letter B tensored with D with some integer coefficient -1, plus its 5 dihedral images, and it's 6 terms long. And the 2 loop 1, which was computed first by Brandhuber, Travellini, and Young, when you switch to this alphabet, it collapses to 12 terms, which are just 2 terms plus dihedral images. And now we have the symbol to 8 loops, where it has 1.67 billion terms, which I won't show you on the next slide. And there's also the 6-gluon MHV amplitude. And we'd been studying that one even earlier. And it has a duality to a Wilson hexagon shown here. And it has a dual conformal invariance. So the variables, the only allowed variables that you can use are conformally invariant ratios of the corners of the polygons, which amount to sort of double ratios of Mandelstam variables, specific ones, u hat, v hat, and w hat. We give them hats to distinguish them from u, v, and w on the form factor side. And there's a similar dihedral symmetry it's actually D6, but the acting on these variables, it reduces to the same symmetry of the form factor D3. And we need to reduce down to a two-dimensional surface, and there's a well-known parity-preserving surface that corresponds to lower dimensional kinematics, and it's defined by this polynomial delta being equal to 0. So the symbol alphabet, as mentioned in Anastasia's talk, she mentioned that there were 15 letters, but if that was in terms of Twister 4 brackets, if you impose a projective invariance, you drop down to 9 letters. And when you go to the surface delta equals 0, the more complicated parity odd letters decouple. And so you again have 6 letters. And we can define the hatted A, B, C up to F's in this exactly the same way as we defined in the form factor case, but now with hats on them. And we can write the symbol of the amplitude on this surface at L equals 1 and 2 loops in terms of the same number of terms as in the previous case, but now involving hats. And some of these coefficients are slightly different, but and this object, before we started these studies, it was calculated at 2 loops by in terms of the symbol by Goncharov, Sproudlin, Vergu, and Volovich, and we've been able to bootstrap it up through, had been able to do it through 7 loops. And then we observed that these two symbols are related to each other by the combination of the antipode map and a kinematic map between the U hat, V hat, and W hat, and the UVW. So this antipode map, as mentioned before, at symbol level, it just reverses the order of all the letters. And it's called a co-inverse for the Hopf algebra. And the kinematic map in this particular case is quite simple in terms of these cross ratios and ordinary ratios, and it just looks like this. And this map has to and does map this plane, U plus V plus W equals 1, to this surface delta equals 0. In terms of the letter substitution map, like we were talking about for abracadabra, the analogous thing is a map from one space of letters, the hatted space, to the other space, and it corresponds to this map here. So square root of A hat, or 1/2 the log of A hat, goes to the log of D. And similarly by cyclic symmetry, and then D hat goes to A. So when you apply those substitutions to those previous 2 loop symbols I showed you, you'll see that they map over to the corresponding case on the other side of the duality. And so that checks it for the 6 and 12 term 1 and 2 loop symbols, but we checked it for all of these cases as well. And you do need to do a little bit of compression to check it at 8 loops. In fact, we didn't exactly check it at 8 loops. We used 8 loops to build the answer on the amplitude side, but it satisfies all the other constraints. So that constitutes a validation to 8 loops. But at this point, we still didn't know exactly why this symmetry was there. But let's see. But then we realized that a way to explain it partially was that it was sitting in a duality, the self-duality for this 4.1. So the self-duality has the form where the antipode map on the 4-point form factor at L loops, when combined with a kinematic map, goes back into the original symbol for that case. And this map is actually pretty ugly in terms of these cross ratios, so I won't show it here. There are some other variables that I'm not going to really define in detail, but they're called the FFOPE variables, and they're introduced by Basso, Sever, and Vieira, or even earlier, and also in work by Sever, Tumanoff, and Matthias Wilhelm. And in those variables, this kinematic map is actually quite simple. There is another variable in the 4-point form factor called F2, but this symmetry works when the 4 momenta are in 3 dimensions. And constraining them to this lower dimensional surface requires F2 to be equal to 1. So I should hurry along now. So we can get evidence for this self-duality by counting. And what you can count is the number of independent coproducts. And when you do this for the 2, 3, and 4-point for-loop answers, and the for-loop one has recently been determined, and it also obeys this property. And you can see as evidence that this sequence of coproducts is palindromic. It's reversible. And that is a necessary but not sufficient condition for the symmetry to hold. And then, as I was saying before, it only holds on 3D kinematics, which can be imposed as this condition with the Levi-Civita tensor, or by setting F2 equal to 1 in this other parametrization. So I should mention that Zhenji Li has also computed higher point form factors for the same operator, for n equals 5 and 6. And he computed the remainder functions. And one of the interests in doing that is looking for antipodal self-duality in these higher point ones. And he found a similar palindromic property for counting the number of symbol letters in each slot. And that looked encouraging. But we've been looking, especially as student Shou Xin looked at whether there's a suitable kinematic map. And we haven't been able to find one yet. So we're quite puzzled. And because of that, we decided to move to a little simpler setting. I want to mention very briefly that Ellis Yuan here, along with Nima, they wrote a paper where they showed that one-loop n-gon integrals, which typically have weight n over 2, they can be mapped into other integrals by the symbol antipode, and it reverses the Cayley matrix here that appears in the Zemancic F polynomial. But this inversion changes the masses of the internal lines. And so we don't quite know whether this property is at all related to what we're looking at, but at least we haven't figured out a way to do it. So I mentioned these ladder integrals, and the ladder integrals were worked out many years ago by Usyukin and Davidichev in terms of only classical polylogarithms and logarithms. And they take this form in terms of these z and z bar that are related to the cross ratios. So if you apply the same game of computing the dimensions of various lower weight spaces, you actually find for the ladder integrals that they have a palindromic property. They look the same backwards and forwards. And so that looks like maybe there is some antipodal self-duality, but on closer inspection, you find that there's no way they can be self-dual, except for the first case, p equals 1, which we already saw was self-dual. Then we can look at the same counting for the 4-point fishnet integrals. And those fishnet integrals we found with Benjamin Basso, and it was later proved in these other papers, that these fishnet integrals, which are labeled by 2 integers m and n, are determinants of a Hankel matrix. That means that the ith and j term in the matrix, it only depends on I plus j. Using this formula, you can count, and you can find that the 2, 2, 1 has this symmetry, and then the 2, 3, 1 does not, but the 3, 3, 1 does. And so that gives you the license to look for this symmetry for the n equals m case, the square fishnets. And once again, here's the 1, 1 symmetry we discussed before, and this kinematic map is the one we want to then apply to the general phi mm. So with Claude Dour, we were able to prove that this function, the square fishnet, is invariant. And the proof has 2 steps to it. under this combined operation S hat, the ladders transform into this linear combination, and I won't go through the proof for lack of time. But if you insert this into the determinant, you find that you can show that it's completely independent of L. L is the log of Z and log of Z bar, and you need to show that it drops out of the expression. If it does, then everything reduces to the L equals 0 version, which is the original expression. So I will skip through this for lack of time, but just say that we have been looking for polynomials and ladder integrals that generalize this, that obey the Steinman relations and antipodal self-duality. And we've found infinite families of solutions to these constraints that are all linear combinations of determinants first defined by Frank Coronado. So there's a pretty picture there. It involves transformations that can all be organized in certain graphical ways. And but I will just wrap up and thank you for your attention.